Welcome, my friends. Linear programming is a technique in which a linear function is maximized or minimized when subjected to various constraints. For example, a company might want to maximize profit, but it might be constrained by the number of employees they have, as well as supplies or inventory on hand. Or maybe a group of hikers are out going for a trip, and they want to minimize their weight to make travel easier. They may be subject to certain nutritional or caloric requirements that need to be taken into consideration. In every linear programming problem, something needs to be maximized or minimized, and is subject to a number of different constraints, usually either restrictions or requirements. I will be solving linear programming problems by graphing in this video. These are long problems and take a lot of organization. I will be splitting the process into 7 steps. First, you need to define your x and y variables. The problems I do will only ever have 2 variables. These variables always relate to something that you either want to maximize or minimize. So if you are maximizing profit by selling computers, x and y will most likely relate to 2 types of computers that you are selling. If you are minimizing cost by producing books, then x and y relate to the 2 different books that you are producing. Write out a sentence to describe what both x and y represent. Step 2 is to write what is called the objective function. This is the equation for what you want to maximize or minimize, and will always, at least for our purposes, take on the form something is equal to ax plus by. The something is whatever you are maximizing or minimizing. So if you are maximizing profit, you write profit is equal to ax plus by, and fill in the values for a and b from your problem. For example, if you are selling 2 types of computers, and you make $50 in profit for the first computer and $75 in profit for the second computer, the objective function would be profit is equal to 50x plus 75y. Step 3 is to write out the system of inequalities related to either the restrictions or the requirements. If you are maximizing something, you will have restrictions, and if you are minimizing something, you will have requirements. I like to make a table at this stage to help me organize the information from the problem, as I will show you later. Typically, you get 2 or 3 inequalities in terms of both x and y, and usually there is a requirement that both x and y are at least equal to 0. Step 4 is to find the x and y intercepts of all the inequalities that you found in step 3. We will use the intercepts to graph, and they will also be useful in a later step. Step 5 is to graph the inequalities from step 3, using the x and y intercepts from step 4. You do not graph the objective function from step 2, only the inequalities from step 3. There will be a region on the graph that is consistent with all of the inequalities. We call this the feasible set. For example, it might look something like this. This area consists of all the possible values for x and y that either meet your requirements or do not exceed your restrictions. We call this the feasible set. It turns out, by what is called the fundamental theorem of linear programming, that the maximum or minimum value of the objective function will always be found at one of the vertices of the feasible set. So one of the intersections of the lines will either be the maximum or the minimum value of the objective function. Step 6 is to evaluate each of the vertices of the feasible set, meaning plug them into the objective function. Usually I make another table for this. Step 7 is to write a concluding statement about which values for x and y maximize or minimize the objective function, based on step 6. Your conclusion should be written out in the context of the problem. For example, you might say that 15 units of product A should be produced and 20 units of product B should be produced to maximize profit to $C. Okay, I know that's a lot of information, but the more of these problems that you do, the more familiar that it gets. Let's take a look at a problem. A manufacturer has the capacity of producing 2 different time machines, basic and galactic. There are 3 phases in the production of these 2 machines. The first is the construction of the components of the machines, the second is the assembly of the units, and the third is the final finish of the machines before they are packed up and shipped to the customer. For each basic time machine, it takes 2 hours to create the components, 2 hours to assemble the machine, and 1 hour of finishing for a profit of $300,000 per machine. For each galactic time machine, it takes 2 hours to create the components, 8 hours to assemble the machine, and 2 hours of finishing, for a profit of $900,000 per machine. Every week, there are 42 hours available for the construction of the components, 90 hours available for the assembly of the machines, and 27 hours available for the finishing of the machines. Find the number of basic and galactic time machines that the manufacturer should create every week to maximize profit. Let's go through the steps. Step 1 is to define your variables, which must relate to what is being maximized or minimized. If we read the last little part here, we see that we want to maximize profit. So ask yourself, how does this manufacturer make profit? Well, by producing time machines, either of the basic or galactic variety. So that means our two variables must relate to the two machine types. We can let x represent the number of basic time machines produced and let y represent the number of galactic time machines produced. Step 2 is to write out the objective function, which is always in the form something is equal to ax plus by. In this case, we have profit is equal to 300,000 x plus 900,000 y, since $300,000 of profit is made for each basic time machine produced, and $900,000 of profit is made for each galactic time machine produced. Step 3 is to write out the system of linear inequalities based on the problem description. I do this with the help of a table. In the table, I have columns for x and y, which in this case are the basic and galactic time machines. Then I have another column to the right, which is either restrictions or requirements. If you have a maximization problem, these will most likely be restrictions, and if you have a minimization problem, these will most likely be requirements. We have a maximization problem, and we have restrictions related to the number of hours available in each phase of production. The restrictions relate to the number of hours available in the 3 phases of production, which are components, assembly, and finishing, so we put these in the first column. You don't really need a title for this column. For the basic machine, we are told that it takes 2 hours to create the components, 2 hours for assembly, and 1 for finishing, so we can fill that into our table. I like to be specific in the table, so I am writing 2 hours per machine. For galactic time machines, components take 2 hours, assembly takes 8 hours, and finishing takes 2 hours. Now, altogether, we are told that we are restricted to 42 hours for components, 90 hours for assembly, and 27 hours for finishing, so those are the values that go in the final column. These values are not per machine, these are the total amount available to make both basic and galactic time machines. Now that we have completed our table, we can create our system of linear inequalities from the table, which is 2x plus 2y is less than or equal to 42, 2x plus 8y is less than or equal to 90, and x plus 2y is less than or equal to 27. We use less than or equal to because we had restrictions. We can't go over the specified number of hours in each department. For my problems, we will always have the equal to part in our inequalities, never just less than or greater than, always less than or equal to or greater than or equal to. We have the additional restriction that x and y must both be positive, as you can't make negative time machines, so we have x is greater than or equal to 0 and y is greater than or equal to 0. You have these last two inequalities in almost every problem. I like to use color on the inequalities, and I would encourage you to do the same if you have different colored pencils or different colored pens. We will eventually end up graphing these, and it's hard to keep track of them if they don't have different colors. Another possible way to differentiate them is by labeling each inequality with a number, such as number 1, number 2, number 3, and then labeling them on the graph that way later. Step 4 is to find the x and y intercepts, which I create another table for. The first column is each of the inequalities in y-intercept form. If you solve each inequality for y, this is what you get. I trust that you can convert each of these inequalities into slope-intercept form without a problem, so I'm not going to show the details. The y-intercepts are obvious once you have the inequalities in y-intercept form: 0, 21, 0, 11.25, and 0, 13.5. The x-intercepts can easily be found by letting y equal 0 in each inequality. For the first inequality, you get 2x is equal to 42, as the y term drops out, and when you divide by 2, you get x is equal to 21. For the second inequality, you get 2x is equal to 90, which becomes x is equal to 45 when you divide by 2. For the last inequality, plugging in y equals 0, you get x is equal to 27. That means our x-intercepts are 21, 0, 45, 0, and 27, 0. You don't have to worry about intercepts for x is greater than or equal to 0 and y is greater than or equal to 0. Step 5 is to graph the inequalities and find the feasible set. We will graph with the intercepts. I like to make a nice scale so that I can fit all the intercepts easily onto the graph. So here I have the x values going up by 10s to account for my largest x-intercept of 45, and the y values I only have going up by 2s, since my largest y-intercept is only at 21. Plot each intercept and connect the dots to draw the lines. We have 21, 0 and 0, 21, which creates the first line. We have 45, 0 and 0, 11.25, which creates the second line. We have 27, 0 and 0, 13.5, which creates the third line. We also have x is equal to 0 and y is equal to 0, but those are just the y and x axes. Now we need to figure out where the feasible set is, the area on the graph consistent with all of the inequalities. For the vast majority of problems, as long as the inequality sign is the same on all of your inequalities, not counting x is greater than or equal to 0 and y is greater than or equal to 0, there are only two options. It will either be this outside area up here, or this inside area in here. You can tell based on the inequality symbols. We have less than on all of the inequalities except x and y, so that means the area consistent with the inequalities is below the lines on the inside. So I can cross off all the other areas of the graph. The inside is what we call the feasible set, which I label Fs. The feasible set has what are called vertices, intersections between the lines. We can see that there are 5 vertices: A, B, C, D, and E. I always label the vertices with capital letters. By the fundamental theorem of linear programming, the maximum of our objective function will be found at one of the vertices of the feasible set. So the maximum profit will occur at one of these 5 points. The 6th step is to determine what these vertices are and to evaluate them inside the objective function to see which one maximizes profit. Here I make another table, the first column of which has the vertices. We need to figure out what the coordinate points are corresponding to each of the 5 vertices. 3 of the vertices you already know: A, D, and E. A is the y-intercept of the green curve, which is 0, 11.25. Now you technically can't make a quarter of a machine, but you could be a quarter of the way through making a machine by the end of the week, so we will allow the partial machine. Point D is the x-intercept of the blue curve, which is at 21, 0. Point E is 0, 0, which is almost never the optimum value for the objective function, but we should write it down anyways. The other points can be found by setting the appropriate lines equal to each other and solving for x and y. To save time, I'm going to be using the TI-84 calculator. If you press y equals, you can see that I have the 3 curves typed in right here. Go to Window and set up a nice window that will allow us to see the graph. I know the largest x-intercept is 45, so maybe I'll set the x-max to 50. The largest y-intercept is 21, so I'll set the y-max to 25. Press Graph and you should see the picture. Now if you press Second, Calc, you have option 5, which is Intersect. Select that option. We want the intersection of the green and red curves, which are the curves with a slope of -1/4 and -1/2. You can tell we are on the wrong curve by the indication on the top left of the calculator. Press down once and you can see we have switched curves. Press Enter to indicate that we want the curve with the slope of -1/4. Now it's asking for the second curve, which we want to be the curve with a slope of -1/2. It looks like the calculator is on that curve, so press Enter, and then enter one more time, and you will see the intersection of x equals 9 and y equals 9. So the point 9, 9 is point B. Let's do it one more time to find point C, which is the intersection of the blue and red curves. Press Second, Calculate, option 5 for Intersect. We need the curves with slope -1 and -1/2. It looks like the calculator is on the right curve, with a slope of -1, so press Enter. We don't want the curve with a slope of -1/4, So press down once, and you will see that we are on the curve with a slope of -1/2. Press enter twice, and we will see the intersection is x equals 15 and y is equal to 6. So a point C is x equals 15, y equals 6. Now we need to plug these points into the objective function to see how much profit is made. If x equals 0 and y equals 11.25, we have 300,000 times 0 plus 900,000 times 11.25, which comes to $10,125,000 if you plug it into your calculator. 9 leads to the value of $10,800,000. 15.6 leads to $9,900,000. 21.0 leads to $6,300,000, and 00 leads to a profit of $0. We can see that the maximum profit is obtained when 9 of each machine are produced, and the profit is $10,800,000. Finally, we are on the last step, which is to write a concluding statement. To maximize profit to $10,800,000, 9 basic and 9 galactic time machines should be produced each week. Okay, we have finished the problem. I know that it's a lot of work, but it only gets easier the more practice that you do. Alright, my friends, that wraps up our video over solving a linear programming problem using the graphing method.